Okay, so a graph is said to be bipartite if you can partition the vertices of the graph into two set of vertices such that all edges in the graph are between the vertices in the two set. Again, it need not be equal size partition. It could be something like this where you have few vertices in one partition compared to the other. The requirement is all edges in the graph should be between, or should be only between the vertices in the two partition. No edge should be between vertices in the same partition. So if a graph satisfies this property, it is said to be a bipartite graph. Now again, not all real world network graphs could be bipartite. It's very difficult to expect like that. So what we could observe is some graphs like this, for example. So most of the edges could be, if at all the bipartite property is existing in that graph, most of the edges in the graph could be between the two partitions of vertices, but there could be still some edges like 1, 3 and 2, 4 that are between vertices in the same partition. So what we want to capture here again is to quantify the extent of bipartivity that is existing in the graph. Okay, so again, if there are no such edges, so these edges between vertices in the same partition has name, they're called the frustrated edges. Okay, so those edges that exist between vertices in the same partition, they're called the frustrated edges. So if a graph doesn't have any frustrated edge, so the graph is said to be really bipartite. So we can say that graph is, let me see this, truly bipartite. That's the name I think they have here. Yeah, truly bipartite. So if there are no frustrated edges and all edges are between vertices across the two partitions, then the graph is said to be truly bipartite. Then we will kind of quantify something called a bipartivity index to capture the extent of bipartivity in a graph. So if there are no frustrated edges in this graph, then the bipartivity index of that graph will be 1. On the other hand, look at these two graphs here. This graph has 1 frustrated edge and this graph has 3 frustrated edges. So the bipartivity index of this graph that has only 1 frustrated edge is 0.829 compared to this edge that has more frustrated edges in both the partitions, and it is 0.645. So more the frustrated edges, especially more frustrated edges among vertices in the smaller partition, the lower will be the bipartivity index. Okay, and I'll again go through this statement which I just made by looking at these different graphs. But basically, the more the frustrated edges you have, you can expect the bipartivity index to be lower. How low the bipartivity index can go? So it can go up to 0.5. So the range of the bipartivity index values for any graph will be 0.5 to 1. So if the graph is truly bipartite, the bipartivity index is going to be 1, and then if you start having frustrated edges as I show here, it is going to start reducing. Now let us look at these graphs here and interpret these numbers. So this graph, so again they have two partitions, one partition has 2 vertices and the other has 3 vertices in all these graphs. Then what is varying across these graphs is just the distribution of the frustrated edges. The edges in between the two partitions are remaining the same. Okay, so both these graphs have just 1 frustrated edge, but you could see this one has 0.829 compared to 0.769 for the other graph. The reason is even though they have just 1 frustrated edge for each, where is that frustrated edge? So for this graph, the frustrated edge is between vertices in the smaller partition, as this one is between vertices in the larger partition, and that's the kind of property that's observed. The more edges that are in the smaller partition, then the lower the bipartivity index. So this graph has a lower bipartite index compared to this graph. So basically the idea is you prefer the frustrated edges to be more between vertices in the larger partition compared to smaller partition. Now look at this graph here, it has two frustrated edges compared to these ones. So again, there are two things to be remembered. So the larger the number of frustrated edges, the lower the bipartite index, as well as if two graphs like this have the same number of frustrated edges, we have to then compare how the frustrated edges are distributed across the two partitions. But for this graph, it has two frustrated edges more than these two graphs. So its bipartite index comes out to be even less than the second one here, or third one, however you want to number it. Now this one has a lower bipartite index than this, even though it has two frustrated edges as this one. Here you see there are only two vertices in this partition on the left side, and both these vertices are connected with an edge. So that's a very poor, it's not a good thing to observe, or because of this, the bipartite index will tend to reduce compared to this graph. So here there's no edge between the two vertices in the smaller partition, and this is a partition of three vertices, and they could still have one more vertex, one more edge between this bottom vertex and top vertex. Okay, but so the maximum number of frustrated edges possible among the vertices in this partition is still not reached. You still have one more edge that you could have between the two vertices in this partition. Whereas here, there are only two vertices in this partition, and you already have an edge to connect them. That's like the best and worst you can have. You cannot have more than an edge in this partition, more than one frustrated edge, and it's already there. So that's the reason the bipartite index of this graph tends to be lower than this one. Now, how about this? So here this edge is missing, and you're just adding this, and that actually reduces a bipartite index further, because as I said, you're now having two of the three frustrated edges that is possible on the larger partition, and that's not good. Okay. Now for this graph, there is no edge in the smaller partition, but it has three frustrated edges, so it has almost the same bipartite index as this one. And this graph has frustrated edges between all these three vertices here and this vertex, so it has the lowest bipartite index among all the graphs here. Okay, so it's now quite interesting or curious to see how to measure this bipartite index, so that we can also get some numbers like this for a graph. Okay, so the approach is quite simple. What we have to do is, again, feed in the adjacency list or adjacency matrix. As I suggested, adjacency list, unless you need to work with adjacency matrix, you could follow that approach. So feed in the adjacency list for a given graph and get its eigenvalues. So let us say lambda 1, lambda 2, lambda 3 up to lambda n, or the n eigenvalues for an n by n adjacency matrix, adjacency list. So the graph is considered to have n vertices. So once you get the eigenvalues, you have to just plug them here in this formula. Sum of the cosine h of this lambda values, which are eigen values, divided by the sum of the cos h of the eigenvalues plus sum of the sine h of the eigenvalues. So you could see this is a ratio, and the denominator has two terms, and one of these terms is only term in the numerator. So then also the cos h and sin h values are related by this property. So for example, let us go through this code, this example. So for this graph, if you compute the eigenvalues, it has 6 vertices, so you're going to get 6 eigenvalues. So these are the 6 eigenvalues. Now the cos h of -2 is 3.7622. So everybody knows how to find the use a calculator to find the cos h. Let us use this. So cos h of -2 is 3.7622. Okay, then you can find for a cos h of -1 and so on. So use the cos h, hyperbolic cosine function. So the cos h values for any eigenvalue is going to be always positive. It could be 0, it could be positive, it cannot be 0, it cannot be less than 0. Whereas the sin h values could be negative as well as positive. So what happens is, if you take the sum of all the cos h values and the sum of cos h plus sin h values, it comes out to be that the denominator, the sum of the cos h plus sin h values, simply turns out to be just the sum of the cos h values. So as you can see from the numbers here, cos h of these lambda values are given here and sin h of these lambda values are given here. So the numerator is the sum of all the cos h values. The denominator is the sum of sin h values plus the sum of the cos h values. So the sum of the sin h values, you can see -1.1752 will cancel up with this 1.1752 positive. Then negative here with positive. Then -3.6269 will cancel with 3.6269. So the sum of the sin h values is going to be 0 if the graph that you begin with is bipartite in nature. Okay. Now we'll see, we'll check. You can use breadth first search to check whether the graph is bipartite or not. So that's one approach. But we will make use of the eigenvalues and eigenvectors to check for the bipartivity of this graph and get the two partitions. But given a graph, we can right away go ahead and feed in the adjacency list or adjacency matrix to the spectral analysis code and compute the eigenvalues of that graph. And then using the cos h and sin h values in this formula, you could get a measure of what is called the Bipartivity Index of this graph. If the Bipartivity Index of the graph is close to 0.5, there's no point in even trying to come up with a bipartite graph involving these vertices. Okay, so that's why it's a good idea to go ahead and measure the Bipartite Index first for a given graph, so that you get an idea of the extent of bipartivity that is possible on this graph. Okay, so any questions so far? Okay, so now what we will do is how to identify whether this graph is bipartite or not. Now look at the number that we got for the Bipartivity Index. So if the Bipartivity Index of a graph is 1, that means the graph is bipartite. Okay, so if it is less than 1, it means the graph is definitely not going to be bipartite. So you could check this with some graphs that you have, and you will find this property to be true. Now once you decide the graph is bipartite, we need to identify the two partitions of the graph. So how to identify the two partitions of the graph using this eigenvalue eigenvector approach? So what we'll do is, we'll take the lowest. So this is one application where an eigenvalue other than the largest eigenvalue is useful and the corresponding eigenvector. So we'll take the lowest negative eigenvalue of -2. So for this graph, if you run this graph with the spectral analysis code, So make sure the last line is blank, not blank. So once you have the results displayed for some file, you don't need to close the program and restart it. Just say open and analyze your file. Of course, the results of this file will get lost. So if you want to save to a file, you can click on saving to a file before that. So load the new graph, and you see here you have 6 eigenvalues because there are 6 vertices. So we'll focus here on the smallest eigenvalue, which is -2, and these are the entries in its principal eigenvector. So now the rule to get the two partitions of this: put together the vertices with odd number in one partition and put together the vertices with even number in the other partition. Not odd and even. Put together the vertices with the odd and even for the breadth first search approach for the level numbers. Okay. So put together the vertices with positive entries in the eigenvector as one partition, and the vertices with the negative values for the entries in the eigenvector in the other partition. So in that sense, we'll observe vertices 2, 4 and 6 to have negative entries. So that's why I show here to be more readable. So the vertices with the negative entries in the eigenvector of the lowest eigenvalue, okay, are considered to be in one partition. So vertices 1, 3 and 5 are in one partition, 2, 4 and 6 are in the other partition. You don't need to worry about the values in this eigenvalue in the eigenvector for now. Any question? So let us do one more example that may be even more clear. So you have our previous graph that we worked on. So I look at the eigenvector corresponding to the lowest negative value or the smallest eigenvalue, and that happens to be 2.487, and these are the entries in its eigenvector. So you can say vertices 2, 4, 5 and 8 form one partition and the other vertices form the other partition. And so this is same as the original graph given to us. Okay, but I've drawn the vertex edges in such a way you can visualize this as a bipartite graph. So this graph and this graph are the same. So it looks like there are only two frustrated edges and one frustrated edge in each partition. So what we want to now do is quantify the extent of bipartivity in this graph. So how to quantify the extent of bipartivity? So for that we need to make use of the eigenvalues. So we have the eigenvalues lambda. Find the cos h and sin h of those eigenvalues. Then the bipartivity index is the ratio of the sum of all the cos h values divided by sum of all the sin h values plus the sum. If the graph is not bipartite, the sum of all the sin h values is going to be positive, not 0. So the denominator is guaranteed to become larger than the numerator if the graph is not bipartite, because you have the cos h summation in both numerator and denominator, but you have sin h summation also. So if the graph is not bipartite, the sum of the sin h values is going to be definitely greater than 0.0, so is going to be positive. So that will make the denominator to be greater than the numerator. The ratio will thus be less than 1. So in this case it's going to be 0.8135. Okay. Now you can also do this bipartite detection for a directed graph. So far we did on undirected, and that's what is commonly used. But you can also sometimes use this for a directed graph. So the idea is just remove the directions for the edges, treat the edges as undirected, and run the bipartite analysis program, compute the two partitions and all this stuff. And once you find the two partitions, redraw the edges between the two partitions, and then assign the directions to edges corresponding to the input graph. And this is what you get. So this is the eigenvector corresponding to lowest eigen value, which is negative. And you can see 1, 2, 3, 4, 5 form one partition, 6, 7, 8, 9, 10 form the other partition. So you have found the lowest eigenvalue and the corresponding eigenvector. So using this, you can find the two partitions and then redraw the edges across the vertices, and that will correspond to original graph. Okay. Any question?